Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And, very good morning, everyone. We are going to continue our second lecture on industrial pneumatics. So, we're going to look into second chapter today. So, we're going to look into pneumatic symbols and circuits. So, for this lecture, we're going to look into components of pneumatic circuits and applications. Hopefully by the end of this chapter you should be able to recognize standard symbols for pneumatic actuators, explain the operation of directional control valve by using valve symbols, and also perhaps able to describe a directional control valve by its name, and perhaps understand how it's works as well. Okay, so I'm gonna help you to go through all those lecture notes, and then I'm gonna look into a few videos that might help you to enhance your understanding as well. Okay, so basically this is a pneumatic system. We've seen this before, I think, in the previous lecture. So we have air compressor, we have the tanks. Okay, just auto drain as well, so if you need to remove from it, and then we have the air compressor, this thing, diesel based air compressor. We have auto drain as well, we have air dryer, line filter actuators. Okay, and then we have air service unit. So this is actually close to the actual actuators. Okay, so remember I've told you before that the air service unit sit close to the actuators. So different actuators might share one air service unit, but all those actuators that share same air service unit should required the same amount of pressure. Okay, so a little bit more about pneumatic actuators. So actuators is a device that converts energy. In this case, the energy from a compressed air into the mechanical energy, such as motion or impact. So if you have electrical actuators, you would convert energy in electrical form into a mechanical energy. Okay. So pneumatic manufacturers classify actuators type by actuator design, such as tie rod cylinders or rodless cylinders. We're going to look into videos on rodless cylinders later. So pneumatic actuators can also be classified by their motion, either linear actuators or rotary actuators. We could also have a grippers and vacuum system as well. So this is the regular linear actuators. You could find something like this in our lab as well. This is rotary actuators. This example is actually not turn 360. So you could have another rotary actuators which actually have the rod here turn 360. And then you have other type of pneumatics, grippers, vacuum system as well, like you've seen before in our previous lecture, that vacuum that suck in that plate, is it? Okay. Okay, let's say this one. Cylinder.
The Aventix RTC Rodless Cylinder Series is available as a basic version, as a cylinder with an ultra-precise rail guide, as a version for high loads, and as a version with slide bearing guide.
No road.
The various possible applications for the RTC are as versatile as its different versions. Move, guide, sort. With forces acting on the side, with intermediate stop, onward movement or backward movement.
So this is neat. Okay.
For high speeds up to 24 meters per second. The rodless cylinders offer optimized stroke lengths in a compact size. This saves space and facilitates machine design. Thanks to its unique design, the RTC from Aventix offers high performance and a long service life. The oval
Aventix
piston
is
absorbs
one of the
lateral torques and doubles the load
We don't
capacity.
have that in our lab.
Scrapers and special seals protect the cylinder and extend its service life. Cushioning pins and enlarged air ducts enable high speeds. With a comprehensive range of accessories, the cushioning and stop can be adjusted along the entire stroke length. Shock absorber settings are retained even when the shock absorber is exchanged. The cylinder also features a pneumatically operated intermediate stop. After a stop, the cylinder can move on in the same direction or move backward to the original position. Two proximity sensors in the same direction are possible. Piston movements are recorded by the distance measuring sensor. This enables an exact query of the slide's position. The RTC rodless cylinder is also available with an ultra-precise rail guide as a compact guide version and as a heavy-duty version for high loads. With the RTC TD, a cylinder that was specifically developed for train door applications, Aventix offers an innovative, inexpensive, all-round solution that is quick to install and maintenance-free. Smooth manual door opening is possible across the entire door width. The RTC, our multi-talent for a wide range of applications.
Okay. So as you can see, there's a different type of application as well. So you can explore that on yourself afterwards. So this is a linear actuator. So pneumatic linear actuators or linear cylinders provide fast moving and good linear force. Okay. In many cases, this is even more reliable than electric. If we are not looking into timely precise motion, pneumatic linear actuator is very good option. The force and motion is produced by pressurized air entering through the port and pushing the piston surface inside the cylinder. Okay, so this is the end. Okay, so the rod is here, so push forward. So this is the barrel where we place those pistons. Okay. So a good design won't allow any air coming out anywhere here. Okay. So the air flows in this direction, and then it will force the cylinder to move in the other direction. If you have a double acting cylinder, you would have two ports. Okay, so one would push in this direction, and then another port here move in this direction. Okay, we'll see later on. There's a spring return cylinders, so they have springs here, so you put in pressure in this direction, and then once you removed the pressure, it would return back to its original position. Okay, we'll look at that later. So this is a single acting cylinder. So one of the types. So we have double acting cylinder, we have single acting cylinder. So for single acting cylinder, the pressurized air acts only on one side of the piston. Okay, so such that the cylinder only move one way with a usable force. So the cylinder will return to its initial position by spring force, which is usually the case, or the gravity. We usually don't simply rely on gravity, except for very specific applications. So most of the single acting cylinder that you have in the lab, not all of them, is actually a spring return single acting cylinder. Okay, so this is ISO symbols for that single acting cylinder. Okay, let's take a look at this. So this is how the pneumatic circuit.
The first example is a simple circuit consisting of a single acting actuator operated by a push button. As you can see, when the button is pressed, the air flows through to the cylinder, pushing the piston rod outward.
So this is
when the button is released,
so
the spring pushes the piston rod back in, and the air in the system is vented through the exhaust.
See it again.
The first example is a simple circuit consisting of a single acting actuator operated by a push button. As you can see, when the button is pressed, the air flows through to the cylinder, pushing the piston rod outward.
Second state will allow this.
When the button is released, the spring pushes the piston rod back in, and the air in the system is vented through the exhaust.
Okay.
Single-acting cylinders have a power stroke in one direction only, either sprung in or sprung out.
Okay.
The simple design only uses air in one direction, saving cost, and can be easily set to return to a known position.
Yeah.
However, they do have limited stroke length, and there is little control on the spring. Single-acting cylinder.
So this is normally retract cylinder.
Have a power stroke in one direction only, either sprung in or sprung out.
Okay. So that sprung out stuff.
The simple design only uses air in one direction, saving cost.
So this one is normally extended. Okay, so when there's no air applied to it, and then extend it. Okay, so there's two types. Okay, so this is how it's look like in our lab. So the buff. This is a limit switch kind of buff. So this is a filter unit. Okay, so this should closer to the actuators.
with single cylinder. You have single cylinder, so you will have one port and one exhaust. And inside there will be springs which will help the piston to come back. Then for single cylinder we will use direction control valve. Now for example here direction control valve is push button. Now what is the name of this valve? We can tell it by the circuit diagram. So what is the diagram? You see two rooms. Two rooms means
So two rooms
positions.
mean you have two positions.
And how many ports do you see? 1, 2, 3. 3 ports. So the valve name will be 3/2 direction control valve. So this is used for single cylinder. So this name will be like 3/2 direction control valve with push button. So when you push, it will activate. So push button. Now for the connections, you have 1 and 2. Okay, 3 is exhaust. 1 is always input. It is from the source. You supply the compressed air, it is from the compressor. So here our 1 is connected to the distributor. This is distributor. You can connect many components through this. And this distributor is connected to FRL or air service unit. What is FRL? F is filter, R is pressure regulator, and L is lubrication, for lubrication. So FRL connected to distributor and distributor connected to 1. So always whenever you see 1, you connect it to distributor for any valve. Like you have so many valves here. Whenever you see 1, you directly connect it to distributor, wherever it is. And the even numbers like 2, 4, 6, 8, so on, they will be output. So they are output. 1 is input, and 3 and 5 odd numbers will be, whole numbers will be exhaust, or 1 is always input. So here we used push button DCV, 3/2 DCV with push button. Now we'll change it with another direction control valve. Both of them are same, but the operator is different. Here we have selector switch. So 3/2 direction control valve with selector switch. Now we'll change it. How it will work, we'll see. Again, direction control valve with selector switch. So the operator
So it would hold.
function will be same, but the operator
So if you notice,
change. So based on the purpose or application, you will change the valves, whatever function or application you are looking for. So
if you have a push button, you need to hold that push button. Once you release the push button, then the valve will be retracted. But if you use that selector switch, it would hold the state of the valve. Okay, that would mean the air would continue pushing the road to be extended until you change.
both of them are direction control valve. If you look from outside, they look same, but if you go in detail, look at the circuit diagram, you will see the difference. So what's the difference? Here 1 is directly connected to 2 without any operation. Here you have to operate the valve to make it connected from 1 to 2. So what will happen if you use this valve? So this valve, it has 2 rooms and 3 ports. So 3/2 direction control valve with push button. But the difference will be, here it is normally open, this one is normally closed.
Close.
So 1 is not connected to 2, so we say normally closed. And this one is directly connected to 2, so normally open. So what will happen if you open the,
It's
you see,
immediately
the piston
extend.
moves automatically. So when you press the button, piston will come back. So it is opposite. So it is normally open. So 1 is supplied to 2, it will work immediately, and once you cut off, it will retract.
Okay. Okay. So now we're gonna look into the operation of single acting cylinder. So basically, I'm gonna re-explain what you've seen on the video just now. So we have pressurized air, it goes in one pot and then it will exhaust to atmosphere. So the air inside here would coming out, and then this pressurized air would move the piston extending, and then once it's fully extended, uh, the pressure would continues to hold that pistons, so that it would go against this spring. Okay, so the cylinders now is fully extended, so the pressurized air in the cylinder, so but no airflow. Okay, now when it's retracting, okay, so we would stop the pressurized air coming into the cylinder, so the spring would push back and then exhaust the air to the atmosphere. So the cap end port is connected to ambient air, so that pressurized air inside the cylinder can be exhausted to atmosphere. Okay, then the spring would push the piston back to its retracted position. Okay. And then now we can look into second linear cylinder, which is a double acting cylinder. So pressurized air acts on both sides. So you have two pot that actually use pressurized air acts both sides of the piston. So it will be usable force applied by the cylinder when both extending and retracting. In this case, you can actually control the position of the piston, so it doesn't have to be fully extending or fully retracting. It could be somewhere in the middle. We could even control the speed as well by varying the pressures on those two ports. Okay. Okay, let's see this.
The second example uses a double-acting actuator. When the button is pressed, air is sent to the back of the cylinder, pushing it out. But this time, when the button is released, air is sent to the front of the cylinder, pushing it back, rather than relying on a spring. Air is exhausted through different ports depending on the position of the cylinder. Best practice would see unidirectional flow regulators to ensure that maximum flow is allowed into the cylinder, but flow is controlled when in the exhaust phase on each side.
Okay. So you can control, I mean, let's say you want that cylinder to extend fast but retract slowly. You can apply this this type of cylinder, because we can control
The second example
the
uses a
motion
double-acting
for each
actuator.
motion. Okay.
When the button is pressed,
Unlike the
air is
spring.
sent to the back of the cylinder, pushing it out. But this time, when the button is released, air is sent to the front of the cylinder, pushing it back, rather than relying on a spring. Air is exhausted through different ports depending on the position of the cylinder. Best practice would see unidirectional flow regulators to ensure that maximum flow is allowed into the cylinder, but flow is controlled when in the exhaust phase on each side.
Okay. So in this case you have double acting cylinder, complex with a complex situation where you have a valve to control the valve. So you have, let's see then.
Now we will move on to a slightly more complex system. A double-acting actuator is operated by an air-piloted valve, which is signaled by two switches. Rather than relying on a spring, this system uses signals from switches to move it both out and back in. This setup
Okay, so
might
it's
be
not
useful if the
spring-knitting.
actuator was located on a roof, for example. Only small pilot lines need to come down to operator level.
Okay. So you have a valve controlled by two valves.
Now we will move on to a slightly more complex system. A double-acting actuator is operated by an air-piloted valve, which is signaled by two switches. Rather than relying on a spring, this system uses signals from switches to move it both out and back in. This setup might be useful if the actuator was located on a roof, for example. Only small pilot lines need to come down to operator level.
Yeah. So for double acting cylinder, so we have pressurized air in one port and then the other port connected to atmosphere. So it will goes extending, and the exhaust goes to the atmosphere. Then we have fully pressurized air in the cylinder, so it would extend fully. Okay, so the cylinder is at rest now. So the pressurized air in the cylinder, but there's no airflow anymore when it's fully extended. When it's retracting, we put in pressurized air in in another port, and then have the other one exhaust to atmosphere. So as the piston is pushed back, the air at the back of the piston is exhausted out through the cap and port. So now the cylinder is back at rest in fully retracted position. So unlike single acting cylinder, the use of pressurized air to extend and retract double acting cylinder has provided cylinders working force to push and pull load. So the push and pull folding door on a bus or on a train, that is one of those application for that double acting. So because it doesn't rely on the spring anymore, we can apply more force because the spring, for that spring return piston is not really that strong. So if you have applied too much load, it won't return back. Okay. So if that is the case, like this one, when we need to apply force on both acting, retracting as well as the extending, like this train or bus door, I think this one is bus door. Okay, here, this one. Okay, so if that is the case, then it's best if you use double acting cylinder, so we could apply more and bigger force on both port while it's extending or retracting. Okay. Okay, let's see this one.
Hohe Geschwindigkeiten, schnelle Zyklen, gekoppelt mit geringsten Stillstandszeiten.
So this is
Highspeed.
quite
Das sind heute Forderungen an
high-speed
Automatisierungslösungen.
application. So if you use pneumatic for linear motion using those cylinders, you could have this. You could achieve this high. So not only high and rapid motion like this one. Okay, this is very much possible with a pneumatic system, but really in this case the loads are small, so there are hardly any delays to the compressed air compress. Okay, if you apply bigger loads, then you might notice some delay on the motion compared to the controlled. Okay, but in this case it's very efficient. Okay. So this is for packaging, I think. Yeah. So you have thermoforming and so you can use that air to apply that immediately. It's quite clean as well because there's no other type of actuators involved, only pneumatics. Okay. Now let's take a look on the rotary actuators. So pneumatic rotary actuators convert compressed air pressure into limited single rotating system. In most cases, it's less than a full 360 revolution. You could have a full 360 revolution, but we don't usually use that. If we need something like that, usually we tend to use electrical actuator instead. So we apply actual electrical actuators and then have the shaft of that electrical actuators to turn whatever stuff that we want to turn in 360 degrees. So until it's unless the requirement is 360, most of the time we can easily use pneumatic. Okay, we could have the one that full 360, but it's not as good as electrical pumps. So if can mix two type of power system, one pneumatic, one electrical power, then we could come out with a lot better. Okay, so pneumatic rotary actuators convert the compressed air pressure into single rotating motion, used for angular motion and as well as changing orientation. So if changing orientation, usually it takes slower because you don't want to break that stuff that you bring over. Okay. Then you have air motors on the other hand that can make full 360 rotation like electric motors. Okay, so that is the one that I was saying before. So for rotary actuators, this is the symbol. Okay, let's see this one. Okay, so we apply the air not simultaneously, alternately. Okay, and then we could turn it as well. So if we apply this one is not spring Newton, this is double acting cylinder. Okay, we can easily control it. Okay, now let's take a look on the control valve. So we have directional control valve, DCV. So this is to extend or to retract a double acting cylinder. So the air flows into the cylinder port mouth reverse direction. So air would be exhausting out. So the DCV are used to control the airflow and direction of pressurized air through the cylinders or any other pneumatic device involved. Okay, so you've seen before in the video different type of DCV. Let's take a look at those different types.
Welcome to Lunchbox Sessions, bite-sized industrial training.
Hello, this is Carl from LunchboxSessions.com. 4-port directional valves are very common for moving a hydraulic cylinder into position, but if that 4-port valve is the type that has 3 positions, a center position, as well as 2 directional positions, how is that center position chosen from among the options that are typically available? Here are 4 of the most common valve centers available to 4-port 3-position valves. We could have a tandem center valve, which will connect pump back to tank while isolating A and B. We could have a float center valve. I think you can see what's happening there, where only the P port is blocked. We could have a closed center valve where all 4 ports are isolated, or we could have an open center valve. So in this particular circuit, we're in a welding shop and large cylinders have been embedded in the concrete floor and are being used to position I-beams and get them lined up just right before the weld is applied where one beam joins another. The circuit as shown is showing valves with open center. That is, the pump and the tank port and the A and B work port are all connected together. So if I go to move the valve for the left cylinder into the extension position, does the left cylinder move upward? No, it does not. There is a large leakage path through the valve center at the circuit on the right. Let's work with the valve on the right, for the cylinder on the right, and notice that the right-hand cylinder will also not raise because there is a leakage path for the pump's flow back to tank through the left-hand valve. So no way to trap any pressure and the cylinders do not rise. In addition to needing to be able to position each cylinder individually to the correct position as we would like, an additional criteria is that we would like to avoid pumping fluid over the relief valve for prolonged periods of time while the cylinders are in their hold position. And we're going to be leaving the pump running, so what can we do with our valve center choices to try and achieve the goal of getting into position as we want to, one valve at a time, without pumping oil over a spring-loaded relief valve, which would just heat the oil and consume excessive amount of electricity for the electric motor turning the pump. So a pair of open center valves do not work. We've already established that. Let's try something else. Perhaps we're thinking that the tandem center valves would be a good choice. So now our valve centers have connected our P to T port, and we're still nicely unloaded. The pump's flow is unloaded to tank whenever we release the valve handles into the center position, but will the cylinder on the left rise when the valve is moved to the P to A position, the extend position? No, it will not. Just like as we were working with the open center valves, while trying to extend the cylinder on the left, all of the pump's flow has a leakage path back to tank through the valve on the right. Same holds true for the other
So you need
direction.
to have both.
Perhaps if we
Not
were to
link.
introduce a valve on the right that blocks the P port, in this particular case I've chosen the float center, what will happen now? When I move the valve on the left into the extend position, will the left cylinder rise? Aha! Yes, it
Oh,
does. The
right.
left cylinder rises because when we go into the extend position, we find out that the pump's flow is blocked over here at the right-hand valve, and so the only path for the pump's flow at that moment is into the cylinder to extend it. So that seems to be working nicely. And our pump is unloaded back to tank whenever the valves are in their neutral position, center position. But what about the valve on the right and the cylinder on the right? Are we able to raise
Okay. So a directional control valve consists of a spool or puppet that slides inside the valve body like a piston inside the cylinder. So the inlet port for compressed air marked with P, and then the exhaust marked with R or S or V. Okay, depend on the labeling. And then you have the outlet port, normally 2 port marked as A and B. If you have more, then you have port 2 or 4 to be connected to double acting cylinder and other devices. Okay, that's for the outlet. So mechanism to push and pull the spool inside the valve. We could either push it, or we could have electric signal used to move that as well, or like the example before we've seen, they're using pneumatics air to actually change the state of the valve. Okay. So here the internal symbols in the DCV. So it's drawn to show possible valve states or position. So it shows how the air flows inside the valve as directed by the valve spool puppet. So let's say we consider a valve with one inlet and one outlet port below. So in this normal state, the puppet block the air flows and the port are closed or shut down. Okay, when when it's operated in operated state, the valve allow the compressed air flowing from input port P to output port A. Okay, so this is the ISO symbol for this valve, this component. Okay, so the normal and the operated state join together like this one. So for the spool valve with 2 inlets and 1 outlet, like this one. So in the normal state, the spool blocks compressed air flowing from port P. This one, okay. But air flows uh, uh, from output port A to exhaust port R. Okay, so the air will continuously flow in what direction. And then when we change the state, in this operated state, the spool is pushed, so the valve allows air flows from port P to output A. Okay, so move in this direction. Okay, so the mechanism that operates or actuates the valve could be a push button, like we've seen before. We have the manual one, which is push it directly, or we have a plunger or switch state. Okay, this one would keep the position intact instead of spring back into the initial position. So you could either have a spring to return the valve to its normal position. You could have the tend to lock position of valve either in normal or operated position. Okay, you could have a rollover as well, like one we've seen in the video, one of those videos in today's lecture. This is also one of the roller lever. Okay, and then we could have this sensors as well. Okay, so we could have pneumatically and electrically operated valve. So pilot operated, this valve is operated or actuated by air pressure. If you have a solenoid one, and then it will be an electrically operated valve. So you can think having electrically operated valve, you can control the valve remotely as part of a PLC system. We can program that solenoid to be actuated at certain time for certain period of time. So that is nice to have. Okay.
This is a 5-way double pilot valve. It's available in 1/8 quarter, 3 8.5 inch BSP. We have a inlet supply here. In this particular case it's quarter BSP. The exhaust ports in this one are 1/8 BSP with 2 outlets, the 2 pilot outlets, both in quarter, and 2 1/8 BSP pilot ends. So the valve is operated from both directions, and in this case it'll operate a double acting ram like this. We'll demonstrate that. Put a supply into the inlet port. To do this, we'll put an air supply in the inlet port of this valve and connect it onto this double acting actuator. And we'll use a 5.2 pilot valve, one of our mini 1/8 M5 valves. Supply in there, and we'll have to put 2 fittings into either end of this unit. Demonstrating the assembly, here's a little 5.2 valve to operate this.
See, so the valve controlled by air.
There, and that's switching this 5.2. You can leave in one direction and operate the other way. You can also use a silencer to go into the exhaust ports, stop any dirt coming in and also cut down the noise. Or we can go to our silencer, exhaust silencer control.
Usually in the lab we already have that applied, so you don't have that much noise from the valve.
Speed in both directions, and also it will act as a silencer to cut down noise and stop dirt.
Okay.
Screwing these in, we can control the speed.
See, so we're gonna slow down when extending, but return fastly, and then we can make both going slow down as well. Slowly extend, slowly retract,
And if we want to, we can increase the
fast,
speed again.
quickly extend, quickly retract. See, so it's very handy.
If you have ever seen a pneumatic or hydraulic system in industry, you may have encountered these types of equipment with these kinds of symbols on them. These are a kind of control valve.
Okay, so this apply to both
There are a
pneumatic
variety of
as
well-known
well
control
as
valves in the industry, such as glove valves, that you can watch our video about it from the link in the description. But today's video is about different
hydraulics
types of
as
control
well.
valves, known as directional control valves or DCVs for short. You may hear of them as solenoid valves or spool valves as well. If you want to know how they work and how you should read and interpret their symbols, stay tuned for the rest of this video, and please subscribe and click the notification bell for more videos like this. The control valves are mostly known by their adjustability and throttling capabilities. But the valves we are going to talk about them are the types that control the direction of the liquid flowing inside the pipe. Directional control valves are used in pneumatic and hydraulic flow control systems. So
Both of them.
there are pneumatic directional control valves and hydraulic directional control valves. Sometimes the hydraulic directional control valves are called spool valves. As we're talking about the basics of DCVs in this video, and there's not much difference in their working principle and symbols, we develop our example based on a pneumatic system. And of course, if you learn one of them, you can easily learn the other. Let's start with this simple pneumatic circuitry and then see which parts does a directional control valve has. The main power of this pneumatic system is coming from the compressed air that is supplied by a compressor. The directional control valve is directing the flow of the compressed air in 2 different directions to open and close this slide gate valve. using its actuator, which is a double-acting cylinder. A double-acting cylinder has an air chamber on each side of it to move the piston back and forth. One of the directions expands the cylinder and closes the slide gate valve to block the material coming out of the silo. And the other direction retracts the cylinder to its first position. Therefore, the slide gate valve is a normally closed valve. Meanwhile, the sound you hear is the air inside the cylinder exhausting from the valve into the atmosphere. Now, let's take a look at the components and simplified mechanism of this directional control valve. This is the body or housing of the control valve, inside of which there are the paths that air flows through them. The holes you see here are called ports. Within the housing, there is a moving part that leads the air toward different ports of the valve and blocks the others. This moving part is commonly referred to as a spool. The component that causes the spool to move within the housing is an electric solenoid. This is the neutral or rest position of the spool. As you may be familiar with solenoids, when it gets energized by a command from the PLC card, the coil will push the spool and thus it will squeeze the spring on the other side. As a result, you see the piston of the cylinder move to the right side. As long as the PLC's commands remains on the solenoid, the position of the spool will remain still, and the compressed air will cause the piston to keep its last position. As soon as the PLC removes the command, the spring will return the spool to its first position, and the air path will be changed. Therefore, the air behind the piston will be carried into the atmosphere via the valve exhaust port. Now it's time to learn how these valves are called and how to read their graphic symbols. This valve is known as a 5x2 solenoid valve, or a 5x2 pneumatic directional control valve. The first digit is for the number of ports the valve has, and the second digit is for the number of states the spool can be in. Reading and interpreting the symbols may seem a little bit challenging sometimes. For instance, this directional control valve has such a symbol. Each square in the symbol represents a position or state.
Okay.
And in each state, some arrows show the path that air can flow through them and at a specific position. As I've mentioned, this valve has 5 ports, and this is the ISO designation of the ports, which is a common practice. But sometimes you may see an alternative designation of the ports in DCVs by alphabets. Indeed, the P is for power or pressure that comes from the air source. The EA and EB are for the exhaust ports, and the A and B are the output ports to or from the actuator. This is the sign for the electric solenoid, and this one is for the spring return. In our circuit, when the valve is in its rest position, this square is active. When the solenoid gets energized and the spool changes position, the other one is active. Generally, the square just beside the solenoid sign is active when the solenoid is energized, and this is a rule of thumb for any directional control valve schematic. In the end, keep in mind that there are a variety of other directional control valves with more complex functions in different applications that we can check them in future videos if you like this one. If this video helped you, please subscribe and hit the like button. I suggest you watch.
Okay. Okay, you can look into other videos that shows how the control valve works as well from this channel. Okay, this is a good one. Okay, so like it was described in the videos, the description of a directional control valve based on the number of ports as well as the number of possible possible valve state. So if you have 2 state and then you have 3 ports, so you mention the port first and then you mention the ways. So you have, let's say you have 3 ports and then you have 2 ways, okay, and then you have a 3 to DCV. If you have 5 ports, 2 state, and then you have 5/2 valve. Okay. If you have 3 state, like the one you've seen before in the videos previously, then you have 5/3. Okay. But I think in the lab we just have up to 2 state, either 3/2 or 5/2. That should be enough for most of the experiment that we're gonna do in our lab. Okay. So if you have there's 2 possible connection to inlet port. One is pressurized air, the other is exhaust. You need to see what kind of application that you want, in which state you want the air coming out, and in which state you want the pressurized air coming in the cylinder. So you need to fix accordingly. Okay, so this is some guideline. So the position of the valve box and inlet ports when the valve is actuated by pressurized air to the operator. You see this one. So once you push, it moves. Is it? Okay. So that's how you could help. That's how you could help yourself to visualize the movement of the valve. So first imagine that the pressurized air input and exhaust output do not move at all, and then once we actuate the valve, and then it would change state to a new one, and then the pressure air would move, and then you can imagine how the cylinder would act, either extended or retracted. Okay. So for a valve with 3 inlet spots, like 5/2 double solenoid valve, this is the symbol. So normal position also indicates that the solenoid on the right side of the valve is operating, and then the solenoid on the left side is turned off. If you use solenoid on both, if you have a spring return one, then one have a solenoid, one is solenoid actuated, the other one just use spring. Okay. So when the solenoid on the left side turn on and the solenoid on the right turn off, the valve would move to right, and then it would change state. Okay. Oh, I think we've seen this before. So there's another additional description to the DCV, which is a 2 valve configuration available, normally open or normally closed. So for this example, you have 3/2 way roller lever valve with spring return. So this is a full name in the birth certificate. Okay, so 3/2 way, that is the valve state in terms of its port as well as its state. Okay, and then you have roller lever, which is how you actuate the DCV, the directional control valve, and then you have spring return on as to show how it's actually going back to its normal position, either it's normally open or normally closed. Okay, so you could say it's a normally open 3/2 way roller lever valve with a spring return, or you could have normally closed 3/2-way roller lever valve with spring return. Okay, either one. Let's see different roller valve.
This is a 3-2 roller valve. It has a valve body, a roller lever, and an internal moving part. This is the cross-sectional view of the 3-2-way roller valve, without the roller lever. Only the moving part, and valve body are shown. Let's now see the animated view of the valve in action. The detailed explanation of each valve position will follow. When the roller valve is not activated, compressed air supply to port 1 is blocked. But port 2 and 3 are connected. That is, air can travel freely between the two ports. Note that port 3 is normally an exhaust port, air escape to atmosphere through this port. Try to trace out the air path of the cross-sectional view and the symbol shown. They both correspond to each other. When the roller valve is activated or switch over to another position, compressed air supply to port 1 is connected to port 2. Compressed air coming out of port 2 can be connected to the input port of the next pneumatic device and activate that device. Note that at this switching position, port 3 is blocked. At this switching position, the valve symbol has an additional part added, to indicate the valve is activated when constructing a pneumatic circuit diagram.
Okay. What is this? Okay, this is the rotary lever valve. I think this is a short one.
Comes off. Little rubber gasket inside there comes off. 2 gaskets goes between the
So you can
cut hole in the panel, which operates this air ramp. Inlet supply.
so when you apply this, so it
Turn the
would
air on.
stay. Okay.
And by operating this valve,
See?
the valve
So
will
until
stay
you
in
turn
one switch
the
position
lever
until such time
switch
you bring it back
to
in.
the other position, it would keep its original position. But you need to use 5-2 valve here, otherwise it wouldn't work like this.
Demonstrating the 3-2 rotary lever valve. Put some fittings into the inlet port and the outlet port. The outlet port gets connected to the piled end of the 5-2 valve air supply. Turn the air on. Latches over.
Okay.
Once again, switching it, we can stay on. It'll
So this 3-2 valve. This is 3-2 valve symbol drawn in a normal position, so it's not actuated. When we actuate it, and the pressurized air enter the cylinder to the cap end. Okay. This is the circuit, and then it would be fully extended. Okay. If you're retracting, you push it. You release the pressing on the push button, it would go back to its normal state. So the 3-2 valve return to its normal position, and the pressurized air inside the cylinder exit through the port to the valve, so it get exhausted to the atmosphere, and then the spring would push the piston back. Okay, so this is quite simple. Not this one. Oh, okay. So this is the circuit you've seen before. Okay. You've seen this video before. So we actually actuate a 5-2. So this is a 5-2 valve, isn't it? So this is 5-2 valve actuated by two 3-2 normally close, the one with push button valve. Okay. So that is the end of our lecture. So can you classify pneumatic actuators? Name and describe the following valve. The left one and the right one. What's the name of this valve? Give a full name, like the full name in the birth certificate kind of name. Draw a pneumatic diagram. Can you draw a pneumatic diagram showing a double acting cylinder? Okay. Okay. Now, for your class assignment, just as a proof of your attendance, just do it like we've done it before in our previous class. Do it in your handwriting. Answer all these 4 questions. Put it in a paper. Take a picture of it. Convert it into a PDF files, and then PDF file of multiple pages if you have to, and then upload it in our uLearn platform later. Okay. You have until Friday to do that, but I would suggest that you should do it as soon as you can, so that you can be ready for the next lecture as well, as well as the face-to-face lecture on Monday. Okay, so that's all. Thank you very much. Until we meet again on the next lecture. Assalamualaikum.